Section 8.1 or 8.2 is about estimating population proportions. The first thing we're going to talk about is checking conditions. So for this example, we have a class that wants to construct a confidence interval for the proportion P of red beads in the container. Recall that the class's sample had 107 red beads and 144 white beads. The problem is we want to check that the conditions for constructing a confidence interval for P are met. And so whenever we are checking the conditions, there are three that we have to check, and that is it random? Is it normal? And is it independent? Alright, so for it to be random, that means that we have taken some sort of simple random sample. And so if we look at the numbers that we have 107 red beads and we have 144 white beads. And if we were to add those together, we would get 251. So there are 251 total beads. And of those beads, we are looking at the red beads. So we are taking a simple random sample of the 251 beads in the container. Alright, to check to see if it's normal, to use a normal approximation for the sampling distribution of P hat, we need to know both n times P and n times 1 minus P, and they both have to be at least 10. And so what we're looking at when we talk about the red beads is our red beads would be the P hat. And so P hat is going to be the 107 out of 251 beads that we're looking at. So we're going to be using n times P has to be greater than or equal to 10, and also n times 1 minus P, which has to be greater than or equal to 10. Because though we don't know what P is, we're going to have to use P hat instead. So we're going to say n times P hat, which has to be greater than or equal to 10, and n times 1 minus P hat, which is going to be greater than or equal to 10. Alright, the n is the 251. The P hat we said is 107 over 251. And it has to be greater than or equal to 10. 251 times 107 over 251, those would cancel, so we would have 107 is greater than or equal to 10, which works out. Over here, we would say 251 times 1 minus 107 over 251, and that has to be greater than or equal to 10. And whenever we do that, we would have 251 is greater, or no, 251 times 144 over 251. And those, of course, would cancel out, so we would have 144 is greater than or equal to 10, and that works out. So it's that means that the counts for successes, which is red beads, and the failures for non-red beads are both at least 10. So then we're going to look at independent. Since the class sampled without replacement, they need to check the 10% condition, and so that means that we have to make sure that if we do 10 times the 251, we would get 2,510 beads, and so we have to have at least 2,510 beads in the population. This example actually comes from something earlier in the book, which you are not familiar with, but it does say in the book that this teacher reveals that there are actually 3,000 beads in the container. So because there are 3,000 beads in the container, and all we had to have was the 2,510, then that means that this condition is satisfied. So all three of these conditions are satisfied. Therefore, it's safe for the class to construct a confidence interval. Alright, so check your understanding. Number 1 says an AP statistics class at a large high school conducts a survey that asks the first 100 students to arrive at school in one morning whether or not they slept at least 8 hours that night. Only 17 students said yes. So we want to check and make sure that the conditions for calculating the confidence interval for the population proportion P are met. So we have to check again that it is random, that it's normal, and that it's independent. So to check to see if it's random, you are talking to the first 100 students that arrive one morning, and so this would not be met because likely you're talking to the same kind of student. Probably a student that gets up early, one that's definitely not going to be late, a student that's actually at school that day. So random is not met for number one. Because this was definitely a convenient sample. So if we look at normal, we have to know that n times p hat is greater than or equal to 10. And we also have to know that n times 1 minus p hat is greater than or equal to 10. And so our n would be 100. Our p hat would be 17 out of 100. And so those would cancel. 17 is greater than 10 or greater than or equal to 10, so that's okay. And then over here we would have 100 minus 1, or times 1 minus 17 over 100. And so that would give us 100 times 83. Those would cancel. We would have 83 is greater than or equal to 10, and that works. So normal is met. We're good on normal. To be independent, it says that it's a large high school, and we are looking at 100 students, and so we would basically be saying 10 times 100, which gives us 1,000. And we can guarantee that there's probably at least 1,000 students because we're talking about a large high school. If you are thinking about that in relation to East High School, we only have about 700, so this is a good bit bigger than us. All right, so for number 2, it says a quality control inspector takes a random sample of 25 bags of potato chips from thousands of bags filled in 1 hour. Of the bags selected, 3 had too much salt. So the first we have to check is random. And so whenever these bags that he chose were selected, was it done randomly? And so we would say that this is met because it doesn't say how he picks the bags. He just takes a random sample. The second is it normal? So does n times p hat, is that greater than or equal to 10? N times 1 minus p hat, is that greater than or equal to 10? All right, so we have 25 bags. We're looking at 3 out of 25. 3 is not greater than or equal to 10, so that is not met. 25 times 1 minus 3 over 25 would be 25 times 22 over 25. Those would cancel. 22 is greater than or equal to 10, so that works. And the last one that we have to check is independent. All right, so because there are thousands of bags of potato chips produced per hour, then the sample that we chose, which was the 25, is less than 10% of the population, and so this is met. So next we're going to talk about standard error. So a standard error is when the standard deviation of a statistic is estimated from data. Basically, with a standard error, say of a sample proportion or p hat, it describes how close the sample proportion p hat will be on average to the population proportion p in a repeated simple random sample of size n. So that kind of segues into what we call critical values. So basically, in this example, you're trying to find an 80% confidence, and you're going to have to do a critical value to do that. Your critical value is going to be the place that's like the rejection line. So if we're talking about an 80% confidence, that means that we are trying to find the middle 80% or the central 80% of our normal curve. So we've got our normal curve. We're always going to assume that the normal condition is met, or we're going to check and make sure that the normal condition holds, checking the 4 different characteristics that we talked about a few minutes ago. So we are trying to find out the 80% confidence. Now, if you think about that, the whole curve is 100%. So we have 100% in the entire curve. We are going to subtract out the 80% that we want, but that leaves 20% that we didn't necessarily want. The line that separates the 80% from the other 20%, basically where your tails would be, is where our critical values are going to be. And we call a critical value a Z star, and the reason we call it a Z star is basically the star is just there to remind you that this is a critical value and it's not a standardized score like we've seen in the past. Now, we talked about how the 20% was what we didn't want, but remember that the 20% is contained within these 2 tails. And so if there are 2 tails, then that means that the 20% would be split into 0.10 or 10%. So we basically are going to find out what is this little area that's underneath the curve but not in what we want. Alright, so if we are doing that, what we are going to do is we are going to try to find the area of 0.1. Now, this is the standard normal, so we can use the standard normal table. So what you're going to do is you're going to go through your table, and I have it here, but you have it on the pink laminated sheet that you got at the beginning of the year, and you are going to try to find 0.1. So you're going to kind of search through and see what gets closest to 0.1. So I see that I've got 0.1s in this row right here in the negative 1.2 row, and so I see that I get pretty close to 0.1000 right here at negative 1.2, and if I were to look up at the top of that row or that column, I would see 0.08. So that means that my critical value would be at negative 1.28 on this side and positive 1.28 on that side. So basically the critical value that we want is 1.28. Now, this is doing it using the standard normal table, but of course you can always use your calculator to calculate this as well. Because we know what we are trying to find, we know what the area is underneath the curve, we're trying to find what the value is at the bottom. We would do inverse norm. And we're going to use 0.9 because we are trying to kind of get rid of this 10% here. So we're basically looking at this line right here. And so everything over here on this side would be the 90% because this counts for 10%. So 0.9, we know it's normal, so our mean would be 0 and our standard deviation would be 1. And if you were to do that on the calculator, you would get 1.28, and then there's some decimals here, but it rounds to 1.28. All right, so next we're going to look at one sample z-interval for a population proportion. So we're going to choose a simple random sample of size n from a large population that contains an unknown proportion p of successes. An approximate level C confidence interval for p is this right here. So p hat plus or minus the z star times square root of p hat times 1 minus p hat over n. You'll recognize this as being standard deviation. If I go back a slide, that is what this is up here. So this kind of gives you the formula for what you would use if you were trying to calculate a one sample z interval for population. So you have your statistic, whatever that may be. In this case, on this side, we're doing population proportion. So that would be our p hat. And then plus or minus the critical value, so this will be your z star, and then your standard deviation of your statistic. So either if you're using a population proportion or if you are using a sample. So we've got p hat plus or minus the z star times square root of p hat times 1 minus p hat over n. You'll notice that this comes from population proportion. All right, so where z star is the critical value for the standard normal curve with area C between negative z star and positive z star. Use this interval only when the numbers of successes and failures in the sample are both at least 10 and the population is at least 10 times as large as the sample. All right, so kind of going back to the beads example that we talked about earlier, we're going to calculate a confidence interval for P. So we have the class that took a simple random sample of beads from the container and got 107 red beads and 144 white beads. The first thing we're going to do is calculate and interpret a 90% confidence interval for P. So our confidence interval is going to use the form statistic plus or minus the critical value times the standard deviation of the statistic. And so for this particular one, we would be using a population proportion. So we're going to use p hat for our statistic plus or minus the z star times the square root of p hat times 1 minus p hat over n. All right, so earlier, remember we found that p hat was equal to 107 over 251, with 251 being the total that we get from 107 plus 144, and 107 being the number of red beads. Whenever you work that out, you get 0.426. Okay, so we will come back to the 0.426 in a minute, but before we do that, we need to figure out what our z star is, so our critical value. Now remember that we are looking at a 90% confidence interval, so if we're thinking about that on the standard normal curve, we would have 90% that we were trying to contain in the middle, which means that we would have 10% that is left in the tails, and so each tail would then be 5%. Which means that we are trying to find the area that would be like to the left of this 5%. So you can use your inverse normal, and this is all to find the z star. You can use your inverse normal with your first number being 0.05, your second number being your mean, which in this case is going to be 0 because we're assuming that it's normal, and your standard deviation of 1. And whenever you do that on the calculator, all right, so you would go on your calculator, do second vars 3 to do inverse normal. Your area is going to be 0.05. Your mu or your mean is 0 and your standard deviation is 1. So then when you work that out, you would get negative 1.645. Negative 1.645. So that means that we're going to use a z star of 1.645 as our critical value. All right, so now that we have our p hat and we have our z star, and we already know that our n is going to be the number of beads that we're looking at, so 251, then we can plug all of that into this formula here. So our p hat we said was 0.426. We're going to do plus or minus the z star, so 1.645, times the square root of 0.426 times 1 minus 0.426 all over 251. Alright, so for the sake of time, I'm going to go ahead and tell you that if you were to plug all of this into your calculator, you would get 0.051. Alright, so then this plus or minus means that you're going to do two separate ones. You're going to say 0.426 plus 0.051, and then 0.426 minus 0.051. And so when you work those out, you get 0.477 for the plus, and 0.375 for the minus, which means that your 90% confidence interval for P would be between 0.375 and 0.477. All right, we need to interpret what that means. And so I know that my writing's not great on here, so I'm going to go ahead and type it so that you can see it maybe a little bit better. It'll be easier for you to get into your notes. So we would say we are 90% confident that the interval from 3.75 to, not 3.75, 0.375 to 0.477 captures the actual proportion of red beads in the container. All right, so for part B, it says the teacher claims that exactly half of the beads in the container are red. Use your result from A to comment on this claim. All right, so for part B, we would say that the confidence interval in part A gives a range of plausible values for the population proportion of red beads. So basically what that means is if we were looking at what we actually ended up with, we would say that it's probably pretty likely to be between 0.375 and 0.477. However, the teacher says that 0.5 is how many beads or half of the container is actually red. But if we look at 0.5 is not contained within our interval that we calculated here. So we would say 0.5 is not contained. So we have reason to doubt. The teacher's claim. All right, so check your understanding. Alcohol abuse has been described by college presidents as the #1 problem on campus, and it is an important cause of death in young adults. How common is it? A survey of 10,904 randomly selected U.S. college students collected information on drinking behavior and alcohol-related problems. The researchers defined frequent binge drinking as having 5 or more drinks in a row 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as frequent binge drinkers. First thing we have to do, or the first thing we're asked to do, is to identify the population and the parameter interest. All right, so for number 1, our population would be the U.S. college students. And then our parameter that we're looking at would be the true population. Let's say who were classified as binge drinkers. Okay, the second thing it asks us to do is to check conditions for constructing a confidence interval for the parameter. So remember that to calculate a confidence interval, you're going to have to check and see if it's random. Then you're going to have to check and see if it's normal. And then you're going to have to check and see if it's independent. All right, so if we read back in there, up here, it said that a survey of 10,904 randomly selected U.S. college students. So the survey was random, so we did meet that. Okay, then we have to check and see if it's normal. So then for it to be normal, then our successes and our failures have to be at least 10. So our successes in this case would be people that were classified as binge drinkers. So there were 2,486 students that were identified as binge drinkers. And so that means that there were 8,418 failures, or people that were not identified as binge drinkers. Because both of these numbers are definitely larger than 10, then we're good to go. All right, so then we're going to look at independence. So remember that to calculate independence, you have to have your number that you're looking at being at least 10% of the total entire population. So if you think about the number that we're looking at, which is the 10,904, 10,904 is clearly less than 10% of all the college students. So then that meets that condition. So all 3 conditions have been met, and so that means that we can construct a confidence interval. Even if one of these conditions was not met, then we could not construct a confidence interval. All right, so then for 3, it asks us to find the critical value for a 99% confidence interval, show your method, and then calculate the interval. All right, so to do this, we would have to calculate what our Z star was. And so if you're thinking about a 99% confidence interval, that means we're capturing the middle 99%, which means that we would have 1% that's not accounted for. That means that half of a percent would be in our tails. We're going to try to find what's left of this 0.5%. So on our calculator, we would go to second, bars, do inverse normal, and our area is going to be 0.005 because remember, you're going to bump that 2 places. Your mean would stay 0 and your standard deviation would stay 1 because we're assuming that it's normal. And then, or we said that it was normal based on the fact that we met all the conditions. And so then we can figure out that our Z star, our critical value, would then be around 2.575. So we'd say around 2.6. All right, so if we are using 2.6, we have to then use our formula that we talked about earlier. So that would be statistic plus or minus the critical value times the standard deviation. All right, so we're going to say p hat plus or minus the critical value, so the Z star, times the p hat, or square root of p hat times 1 minus p hat all over n. All right, our p hat is going to be the number of successes, so 2,486 out of the 10,904. When you work that out, oh, my sister's graduating from college. Sorry, I didn't mean to hit that. You would do 2,486 divided by 10,904. And you would get 0.279. So let's say 0.22 or 0.2279. So let's say 0.228. All right, so we would say 0.228 plus or minus the 2.6 times the square root of 0.228 times 1 minus 0.228. And all of this is underneath the square root, but also over the n, which would be the 10,904. All right, to make life easier, let's say 0.228 plus or minus. Let's put all of this in the calculator so we can see what that is. So 2.6 times alpha y equals to get your fraction. Oh, actually, let's back up a step. Square root, and then let's do your fraction. So let me get rid of this. Alpha y equals to get my fraction underneath the square root. Oh, go back. And so on top, I would say 0.228 times 1 minus 0.228 all over 10,904. And when you do that, you get 0.014. 0.0104. And so I'm going to split that up into 0.228 plus 0.0104 and 0.228 minus 0.0104. 0.228 plus 0.0104 gives me 0.238, and then 0.228 minus 0.0104 gives me 0.2176. And so what that means is our interval would be from 0.21, let's say 8 to 0.238. All right, 4 says interpret the interval in context. All right, so to interpret this in context, we would say we are 99% confident that the interval from 21.8% to 23.8% captures the true proportion of U.S. college students who would be classified as binge drinkers. All right, so for confidence intervals, a 4-step process for confidence intervals would be to state what parameter do you want to estimate and at what confidence level. The plan would be to identify the appropriate inference method and check the conditions. The do would be if the conditions are met, perform calculations. The conclude would be interpret your interval in the context of the problem. So we're going to move on to an example where we're going to go through that 4-step process. So we are going to calculate the confidence interval for P. So the Gallup Youth Survey asked a random sample of 439 U.S. teens aged 13 to 17 whether they thought young people should wait to have sex until marriage. Of the sample, 246 said yes. Construct and interpret a 95% confidence interval for the proportion of teens who would say yes if asked this question. So this section has a lot of hard-hitting topics that we're covering: binge drinking in college students and now teenage sex. So I'm really glad I'm not looking at your faces right now. So the first thing that you're going to need to do is you're going to state your thing that you're kind of looking at. So you have to talk about what the parameter is that you're going to estimate and at what confidence level. So for your state, you're going to say we want to estimate the actual proportion P of all 13 to 17-year-olds in the United States who would say that young people should wait to have sex until they get married. And we're going to calculate this at a 95% confidence level. All right, so for your plan, you have to, you're going to eventually use a one sample Z interval for P if the conditions are satisfied. And so the conditions that you have to check are going to be, is it random? Is it normal? And is it independent? Alright, so in our problem, it tells us about whether or not it's random. So it says they asked a random sample of 439 U.S. teens. So is it random? Yes, it's random. Alright, so then to check and see if it's normal, you're going to have to look at your successes and your failures and make sure that they are both at least 10. And so our successes would be the 246 that said yes. So 246 is definitely greater than or equal to 10, so that's good. Our failures would be those who said no. And so that would be your 439 minus 246, which would give you 193, and that's also greater than or equal to 10, so normal is met. Then we need to look at independent. So the responses of individual teens need to be independent. Since Gallup is sampling without replacement, we need to check that the 10% condition is met. So the 10% condition would mean that we have 10 times however many we surveyed, 439, and that gives us 4,390. So 4,390 would be the U.S. teens aged 13 to 17. So because we have more than 4,390 U.S. teens between the ages of 13 to 17, we're good to go. All right, so the next thing you have to do is your do step. So your do step is going to be to calculate a 95% confidence interval for P. So to calculate a 90% or 95% confidence interval, you are going to have to know your P hat. And so your P hat would be your 246 over 439. 246 divided by 439, which gives you 0.56. You also have to know your Z star. So to calculate your Z star, you're going to say, okay, I have, and that is really crooked, but I'm sitting on the couch, so bear with me. So you have your normal curve, and you are containing 95% in the middle, which means that you have 5% that is not counted for in your tails, and so each of your tails would be 2.5%. All right, so that means that you are going to be finding the area that is to the left of this point, or 2.5%. So to do that, you're going to do inverse normal. You're going to say that your area that you are looking at is to the left of 0.025, because I would move that decimal 2 places. My mean is going to be 0, and my standard deviation is 1 because we said it's normal. It met all those conditions. So then I go to my calculator, do second bars, inverse. The area this time is 0.025. Standard deviation and your mean are good on this one. So I hit paste. And I would get negative 1.9599. So let's say negative 1.96. We are going to look at the positive of that. So our Z star would be 1.96. All right, we're not done yet. Now we have to use the P hat plus or minus the Z star times the square root of P hat times 1 minus P hat all over N. So that means it's going to look like 0.56 plus or minus 1.96 times the square root of 0.56 times 1 minus 0.56 all over n, which is 439. Alright, so I'm going to do 0.56 plus or minus, go to the calculator, do 1.96 times the square root, alpha y equals 0.56 times 1 minus 0.56, all over 439. When I do that, I get 0.046. Remember, this plus or minus means I'm doing 0.56 plus 0.046 and 0.56 minus 0.046. So on the calculator, 0.56 plus 0.046 gives me 0.606. And then I'm going to do 0.56 minus 0.046. And that gives me 0.514. So that means that my confidence interval would be between, or 95% confidence interval would be between 0.514 and 0.606. And the last thing that we have to do is conclude. So when we conclude on this one, we are basically just interpreting what our confidence interval is. So we would say we are 95% confident that the interval from 0.514 to 0.606 captures the true proportion of 13 to 17-year-olds in the U.S. who would say that teens should wait until marriage to have sex. Alright, so this section of your notes gives you the calculator way that you can construct a confidence interval for an unknown population proportion. So this one goes through and gives you what you would use for the steps and the information that we used in the last example. So it says we'll demonstrate using the previous example of n equals 439 teens surveyed. X was equal to 246 that said that young people should wait to have sex until marriage. To construct a confidence interval, you guys have a TI 30 or TI 84. So you would do stat you would go all the way over to test, which we haven't done yet. You would go to 1 prop Z interval. So you're actually going to scroll until you get to the letters, and you're going to do, and that's alpha A. Alright, so then your X is going to be 246. Your N is going to be 439. Your confidence level that you are looking at is 0.95. So then you would just calculate. Oh, it went away. So then you would calculate and it would give you what you needed. So one more time, Go to stat, go all the way over to test, go to alpha A. X is your successes, so 246. N is how many people you're looking at total or survey total. Your C level is your confidence level. Go to calculate, and then it pops up here and gives you your intervals. So much easier than going through all that process that we just did. Surprise. All right, so sample size for a desired margin of error. To determine the sample size N that will yield a level C confidence interval for a population proportion P with a maximum margin of error ME, solve the following inequality for N. So you've got Z star times the square root of P hat minus 1 minus, or times 1 minus P hat all over N, and that has to be less than or equal to your margin of error, where your P hat is a guess value for the sample proportion. The margin of error will always be less than or equal to the margin of error if you take the guess P hat to be 0.5. All right, so we are going to be determining sample size. So in this example, it says a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion P of customers who are satisfied, that is either too satisfied or very satisfied, the two highest levels on the 5-point scale. She decides she wants the estimate to be within 3% or 0.03 at a 95% confidence level. How large a sample is needed? So the problem is we are going to determine the sample size needed to estimate P within 0.03 with 95% confidence. Okay, so we are going to find first our Z star, so our critical value. Now we're looking at 95%. So again, 95 is in the middle. That means that there are 2.5% on each side. Go to your calculator, second bars, inverse. That would turn out to be 0.025. Mean is 0, standard deviation is 1 because it's normal. And that gives you negative 1.96. But we're looking at we're looking at this right here, so we're saying positive 1.96. Okay. Because you are trying to calculate the sample size, you're going to use that formula that was on the last slide. So Z star times the square root of P hat times 1 minus P hat all over N has to be less than or equal to your margin of error. All right, so we know that our Z star is 1.96. We don't know anything about our P hat. That's what we're trying to figure out eventually. And what we're trying to find out is our sample size, which is N, so we leave that. So basically, all of this is going to stay, which seems really strange. But then we're going to exchange this ME for this 0.03 that was our margin of error. All right, so now you're going to have to do some good old-fashioned algebra. Now, the easiest thing for us to do, our goal is to try to solve for N because that's our sample size. And so the easiest thing for us to do right now is to get rid of all of this square root stuff. So let's multiply both sides by the square root of N. And to multiply both sides by the square root of N is going to do two things for us. Get rid of the square root, and it's also going to get rid of the fraction. All right, so when we do that, that cancels and that cancels out this N and the square root, so we end up with 1 0.96 times p hat times 1 minus p hat, and all of that is less than or equal to 0.03 times the square root of n. Now remember, our goal is to get n to be by itself, so we're going to divide both sides by 0.03 so that that cancels. Okay, so then we have all of this. Remember that this is really 1.96 over 0.03, and all of that is being multiplied by p hat times 1 minus p hat. And this, at this point, is all less than the square root of n, less than or equal to the square root of n. So our goal is to try to get n by itself, so now I'm going to square all this. And so what that turns out to be is 1.96 over 0.03 squared times p hat times 1 minus p hat less than or equal to n. All right, now we have to kind of think about this p hat. And so the largest value of n will be required if p hat is equal to 0.5. Since that will make the product p hat times 1 minus p hat as large as possible. And the reason we do that is because if you think about it, p hat times 1 minus p hat, if your p hat was equal to 0.5, would be 0.5 times 1 minus 0.5. And so that would be 0.5 times 0.5. Because we have no idea of the true proportion P of satisfied customers, we decide to use P hat as 0.5 as our guess. So we're going to just kind of guess that P hat is equal to 0.5. The sample size is, or the sample size required would be all this stuff and then we're going to exchange our P hats for 0.5. And so whenever you work all of that out, you should get 1067.111 less than or equal to n. And so because we are talking about people here, that means that our n would have to be greater than or equal to 1068. So we would want to have 1068 respondents to ensure that the margin of error is no more than 3%. Check your understanding. Refer to the previous example about the customers or the company's customer service satisfaction survey. Number 1 says, in the company's prior year survey, 80% of customers surveyed said they were satisfied or very satisfied. Using this value as a guess for P hat, find the sample size needed for a margin of error of 3% at a 95% confidence level. All right, so what we would need to do for this is we would use our formula that we just talked about. So our z star times square root of p hat times 1 minus p hat all over n, and it all has to be less than or equal to our margin of error. All right, well, our z star has to do with our confidence level, which is 95%. And if you look back, we also had a 95% confidence level. Here, which gave us a z-star of 1.96. Now the good news is our p-hat, they go ahead and give to us, which is this 80%. So our p-hat is 0.8. So for this one, we're going to say 1.96 times the square root of 0.8 times 1 minus 0.8 over n. We don't know what n is. Less than or equal to 0.03 because it's a margin of error of 3%. Our goal is to figure out what n is. So honestly, here's what I think is easiest. I think it's easiest to divide both sides by 1.96. And so when we do that, that cancels. That gives us the square root of 0.8 times, let's do this. Not that again. 0.8 times 1 minus 0.8. So 0.16 over n, less than or equal to 0.03 over 1.96. Then I think it's easiest to square it. So we square that. We get 0.16 over n, less than or equal to on the calculator, alpha y equals. To get our fraction, we're going to do 0.03 on top, and on the bottom, we're going to have 1.96. And then we're going to get out of here and square all that. So when we do that, we get let me go back. Bump that 4 places. So 0.0002, 1, 2, 3, 4. 3, 4. All right, then I think it's easiest to multiply both sides by n to get rid of the fraction. So that cancels. You get 0.16 less than or equal to 0.00234 times n. Divide both sides by 0.00234. Alpha y equals, to get your fraction, 0.16, 0.00234. Oh, I'm missing 0. There we go. Look, it's 1 o'clock in the morning. Bear with me. Alright, let me go back to this. And let's add a 0. So we get 683 has to be less than or equal to n. Basically, your n has got to be greater than or equal to 683. All right, 2 says, what if the company president demands 99% confidence? Instead, determine how this would affect your answer to question 1. All right, so if you think about it, if they are now requiring 99% confidence level, then that's going to cause your sample size to have to increase. And so part of that has to do with your z-star. So your z-star, your critical value, is now going to have to do with 99%. So you would have to go to your calculator, go to second bars to get your inverse. Remember, you're doing 99%, which leaves you 1% for your tails, and so 0.005 would be what you would have as your area. Your mean would be 0. Your standard deviation would be 1. And so when you did that, you would get negative 2.575 or negative 2.58. But you are looking at stuff to the left, so your z star would actually be the positive version of that. So 2.58. All right, so then whenever you plug it into that formula that we just did, so the z star times the square root of p hat times 1 minus p hat all over n has to be less than or equal to your margin of error. Your z star would be 2.58 times your square root. Your p hat would be 0.8 still, so 0.8 times 1 minus 0.8 all over n less than or equal to 0.003. Too many zeros. 3%. There we go. All right, so then you would divide both sides by 2.58. Those cancel. Square root of, what do we say this was up here? 0.16. 0.16 over n less than or equal to so you get let's say 0.012. Squared. So 0.16 over n less than or equal to 0.012 squared. So bounce that 1, 2, 3, 4. That would be right. So then multiply both sides by n. That cancels. 0.16 less than or equal to 0.000144 times n. Divide both sides by 0.000144. Those cancel. Alpha y equals 0.16 over 0.000144. So your n would have to be greater than or equal to basically 1,112 because you are talking about people. And so that is quite a big difference if you are looking at, if you're comparing the two. So you had 683 and now you're jumping all the way to in the thousands. So quite a big difference.